AP Calculus AB, Unit 9, Day 7, Office Hours. These are the answers. Pause the video, quickly check them. Hopefully you've checked them already, but you're definitely going to have some problems like this on your upcoming test. Area between curves. And this just shows the setups, but you still have to find the areas. And there's a couple different ways you could do each problem. You can do them vertically or horizontally. Some of them you're told to do both. Some you're told to do either, or one or the other. These ones you're allowed to use graphing calculator but you gotta set it up first, and then you can use your calculator. And there are some different possible approaches. You could try and do them by hand, just as an extra challenge, if it's doable by hand. All right, so let's try these problems. Okay, first one, we're going to find the area of this region. So we could, this part B says to do it in terms of y, so I assume we should probably just do part A in terms of x. So if you're doing vertical slices, the slice is y top minus y bottom, gives you the dimension of the rectangle. Imagine these are rectangles. And so the area is going to equal, we're going to go 0 to 2 left to right. We've been pretty much given the intersections. And we could find those if we needed to ourselves, right? If you said, all right, 2x equals x squared, move everything one side, equals 0, factor it, right? This is x0, y0, x2, y4. So it's going to be 2x minus x squared is the height of your rectangles. The width is the dx. That's what the dx is for. So find the antiderivative. And then you got to plug limits in. So we plug 2 in, we get 4 minus 8/3. Minus you plug 0 and you get 0. A lot of times you just get 0. That doesn't mean to just always blow it off, because sometimes you don't. Okay, so we could give these least common denominator 12. This would be 4/3 or 1 1/3. Okay, now we're going to try and do it. Determine an integral in terms of y to find the area. Let's see if we can do it. Now, if we're doing y, we're doing horizontal slices. I think it's really helpful to write this. And the dimension now of the rectangle is going to be x right minus x left. But, and I mean, you could write it like that to start with. You could say, okay, it's going to be x right minus x left dy. The problem is that these need to be written in terms of y to actually integrate with respect to y. So we got to get this right here to get x in terms of y. It's going to be plus or minus. It's going to be the positive square root of y, because it's the right half of the parabola. If we were over here on the left half, it'd be the negative square root of y. And then this one right here, x left, is going to be y over 2. So x right is square root of y. X left is y over 2. dy, we're integrating bottom to top now, 0 to 4, not 0 to 2. So the antiderivative is y to 3/2, divided by the new exponent, multiplied by the reciprocal, minus y squared over 4, because there's already a 2 there. And then we're going to plug 2 in, plug 4 in. Do the 1/2. Square root of 4 is 2, cubed is 8. That's going to be 16 thirds minus 4. These common denominator. 16 thirds minus 12 thirds is 4 thirds, or 1 1/3. Hey, what do you know? Same answer, right? So you kind of know if you're trying to do it both ways, you'll know if you got it right or wrong. At least one of them, if they don't come out the same. Let R be the first quadrant region bounded by these two functions. So we should draw a sketch for sure. I mean, pictures are so helpful on these, and these are only going to get more complicated. So it's just good practice. So the square root function looks like this. So you guys should just know that right away. It's the top half of a sideways parabola, and this is a line that goes through 0, 0, and then it's up 1 over 3. So, I mean, we'll just roughly graph it. It doesn't need to be perfect. So there is an intersection point. So we're going to need to find the intersection point. This is the area we're trying to find right here. So we got to find the intersection point. So 1 is probably 0, 0, but we should do the work. So we're going to set 1/3 x equal to the square root of x, and to solve radical equations back in algebra 1, you'd isolate the radical, square both sides. So that's 1/9 x squared equals x. I probably would just like to get rid of the fractions and move everything to one side. X squared minus 9x equals 0. Factor it, x minus 9. So x equals 0 and 9 are the x coordinates of the intersection. So to get the y coordinate, you plug that into either equation and you get the y. This one is 9, 3. Square root of 9 is 3. 1/3 times 9 is 3. Should give you the same thing for both equations. So we got our intersections. So we're going to do it with dx and dy. And then we're going to find the area, I guess, with either one. So this is just saying set it up. Just got to set it up. And then part B is do it. One or the other, I guess. Or both, just to see if you're good at it. Which you probably aren't yet. So more practice will help you get better at it. So if we're doing vertical slices, I like to draw a vertical slice. You need y top minus y bottom, right? I mean, you could even start with that. You can say, okay, I'm going to do y top minus y bottom dx. But we need these in terms, everything needs to be in terms of x. So y top in terms of x is the square root of x. And y bottom in terms of x is 1/3 x. And the limits need to be x, left to right, 0 to 9. So that's with dx. If you can do horizontal slices, just draw one. X right minus x left, give you the length of that rectangle. You could start with writing that if you want. The other dimension is the dy. We're going bottom to top, so 0 to 3 are the limits. X right. X right is going to be, if you solve this for x, it's going to be 3y. And x left is going to be y squared. If you just solve for x, you square both sides. So x right is 3y. Minus x left is y squared dy. So those are the setups. Now let's get the answer. I think that one looks like it's more easier to do. Just, this one's going to have lots of fractions and stuff. But this would be x to the 3/2 divided by the new exponent minus 1/3 times x squared over 2, 0 to 9. So it's going to be, I'm gonna start doing some of the math in my head. Square root of 9 is 3. Cubed is 27. Divided by 3 is 9. Times 2 is 18. Minus 81 divided by 3 is 27 over 2. You plug 0 and you get 0. So we could do least common denominator. 36 minus 27 is 9/2, or 4 1/2. This one seems a lot nicer. 3y squared over 2 minus y cubed over 3, 0 to 3. No rational exponents. That seems nice. This is going to be 27 halves minus 27 over 3 is 9. And you plug 0 in. Happens to be 0 this time. 27 minus 18 is 9 halves. 4, 4.5. Same answer. Should be the same. Same area. Just slicing it up different. Okay, number 3. Find this area right here. These are already written as x in terms of y. So this is set up very nicely, I think, for horizontal slicing. So, I mean, if I had a choice, which it, I guess it seems like we could. I mean, we could do it either way. I'm going to just start with horizontal slicing. So that would be x right minus x left. X right minus x left dy. We already have the intersection points, which we could also find ourselves if we want to. Be y cubed equals y squared, y cubed minus y squared equals 0, y squared, y minus 1. So you can get y equals 0 and 1. Those are the y values, though, which is interesting. So you plug y equals 0 in here to get the x, 0, 0. You plug y equals 1 in here to get x equals 1, 1, 1. Okay, so x right is already nicely written for you. It's y squared minus x left is y cubed dy. And the limits are 0 to 1. So that's the setup. So then the antiderivative is y cubed over 3 minus y to the 4th over 4. 0 to 1. So we get 1/3 minus 1/4 minus 0 minus 0. So that's going to be 4/12 minus 3/12. It's going to be 1/12. So that was with horizontal slicing, and it was set up kind of really nicely, ready to go for that. Vertical slicing, which you might feel more comfortable with, well, probably for sure feel more comfortable with, does require extra work this time because that means you got to get. I mean, we could start it. We say, okay, it's going to be y top minus y bottom. Gives you the height of the little slice, the little sliver of rectangle. Dx is the width. And we're going to go 0 to 1. Coincidentally, the same x's as y's, but we got to get y top in terms of x. So y top is going to be the cube root of x, right? And y bottom, to get that by itself, would be plus or minus, but it's going to be the positive because it's the top half of the sideways parabola. So it's going to be a square root of x. So it's going to be cube root x minus square root x dx. So that was extra work. Now to integrate this, it looks a lot uglier than this one too. Another reason maybe to do it the other way if you have a choice, but let's just try it both ways. So this is x to the 1/3 minus x to the 1/2, which is going to give you x to the 4/3 divided by the new exponent minus x to the 3/2 divided by the new exponent. And then we're going to go 0 to 1. So that's going to be 3/4 minus 2/3 minus 0 minus 0. That's going to be 9/12 minus 8/12 is 1/12. Same answer. That's good. You really probably want to try these both ways as much as you can to get really good at it and to also confirm you're getting the right answers. Okay, A, we're going to do dx and dy, and then we're going to find the area. So if you're going to do dx, draw a slice, y top minus y bottom. What you need to recognize right away is that you're going to have to break it up and do a different y top minus y bottom right here. You're going to need two different integrals to do vertical slicing because the top and the bottoms aren't the same the whole time. The other thing we need to do is we got to find these intersection points right away for either approach. So, so if x equals x squared over 4, so that's going to be x squared minus 4x equals 0. So it's going to be x minus 4 equals 0. So it's going to be x equals 0 and 4. Intersections between these two. Well, this is obviously at 0, 0, 0. If we're to keep going, that's where the 4 comes in, which is not what we're interested in this time. So you got to realize that sometimes you're getting intersections that aren't even on the picture that you're looking at. These two are going to be, if you set these equal to each other, this is x equals 1. That's super easy. Plug 1 into either one and you get the y value. And then these two are going to be what? These are equal. So that's going to be x squared over 4 equals 1. So x squared equals 4, square root of both sides, plus or minus, x equals plus or minus 2. This is obviously positive 2. So I have all the intersections. Now, to do the area with vertical slicing dx, I'm going to need to do y top minus y bottom. And here, that's going to be, in terms of x minus x squared over 4 dx. The limit is going to be 0 to 1. But then you got to do a separate one for this one right here. Y top is 1 minus y bottom is x squared over 4 dx. The limits here start here and end here, 1 to 2. So that's the setup for dx. The setup for d, which looks like a lot of work if you're going to finish it off. The setup for dy, draw one slice, it's going to be x right minus x left. The nice thing about this is it's the same all the time, so you only need one integral. You got to solve this guy for x. It's going to be 4y square root of both sides plus or minus. It's going to be positive. So it's going to be positive 2 root y. Over here, x left is easy. It's just y. So x right is 2 square root of y. X left is y. The limits are in the y direction, bottom y to top y, 0 to 1. And that's the setup for horizontal slices. Way less complicated, right? Way less complicated. Now, to find the answer, I think this one's going to be a lot easier to do the work for, too. It's going to be y 3 halves divided by the new exponent minus y squared over 2, 0 to 1. Plug 1 in, you get 4 thirds minus 1 half. Plug 0 in, you get 0 minus 0. And that's going to be 8 sixths minus 3 sixths is 5 sixths. It's hard to say for some reason. Okay. Now, if you're going to do it the other way, I think it's going to be a bit more work. You're going to have to do x squared over 2 minus x cubed over 12, 0 to 1. And then you're going to have to do x minus x cubed over 12, 1 to 2. You got to do two separate integrals. This one's going to be 1 half minus 1 12th minus 0 minus 0 plus this one's going to be 2 minus 8 twelfths minus 1 12th. I mean, this is a lot. There's a lot more little numbers and stuff than that nice quick one. Okay, what's the easiest way to distribute the subtraction? That goes away. So we're going to have a plus 1 12th here and a minus 1 12th here, so they cancel each other out. And then we have a 2 minus 1 is 1, plus 1 half is 3 halves, minus 8 twelfths, which is divided 4 out 2 thirds. But then when we at least come down, that's going to be 9 sixths minus 6. Hold on. Let's just make sure I did all this right. 9 minus 4 sixths is 5 sixths. Eventually you get the same answer. But I mean, come on. That horizontal slicing was the way to go. The only reason you're not going to do it right now if you had the choice, is because you just don't feel like you're good at it. But if you're good at both of these equally, that is so much less work and probably less mistakes. Okay, let's try this one. Let's just start with vertical slicing, which looks pretty nice. Y top minus y bottom. All right, so the area is going to be y top minus y bottom. Remember, these are all area questions. It better never come out negative. If it comes out negative, something's really wrong. So y top minus y bottom. We need to find the intersections, right? So the intersection, I mean, this is just the cosine curve, so that's 0, 1. And this is the bottom of the sine curve, which is 0, 0. The intersection of the two, where does cosine x equal sine x? What's the angle? Alpha equals pi over 4. They're both root 2 over 2, right? In quadrant 1 and quadrant 3. This is obviously quadrant 1. So this is pi over 4. The y value is root 2 over 2 for both of them. Okay, so if we're going vertical slices in the x direction, we start at x equals 0 and at x equals pi over 4. Y top is just the cosine curve in terms of x. Y bottom is the sine curve in terms of x. So that's your setup. So the antiderivative of cosine is sine. The antiderivative of sine is negative cosine. Plug pi over 4 in, so you can get sine pi over 4 plus cosine pi over 4 minus sine 0 plus cosine 0. Now cosine 0 is not, see, this is a good example. Sine 0 is 0, but this is 1. Now these are both root 2 over 2 minus 1. So it's 2 root 2 over 2 minus 1. So it's root 2 minus 1. Simplified answer, exact. Okay? Now let's see what it would look like if we do horizontal slices. It definitely looks like more work because we're going to have to set up 2 different integrals, right? And I definitely have to set up 2 different integrals. The area is generally x right minus x left. But we're going to have to break it up. So we're going to have to do, now we got to get this. This is like y, right? We got to solve this in terms of y. So that'd be x equals inverse sine of y. That's that x right. This one up here, x equals inverse cosine of y. That's that x right. So x right for the first chunk, working from the bottom to the top, 0 to root 2 over 2 is inverse sine of y, and x left is 0. You could write minus 0, you could just not, plus root 2 over 2 up to the top 1, so the inverse cosine of y. We could clean this up a little bit. The thing here is that you can't, other than it seeming a little more complicated because we would set 2 different integrals, you also cannot integrate these inverse sine and cosines. Like, no, we learned that. No. We know the derivative of inverse sine and cosine. We don't know the antiderivative. Cool thing is your calculator could totally do it. Let's see if our calculator gets the right answer, because your calculator isn't using derivative rules. It's just doing slices that are 0.001, thick. So it's doing estimation techniques. So we do math 9, inverse sine, and we're going to put x's. Even though it says y's, our calculator just does x's. So anywhere we see a y, we're going to do an x. So that's the first one. And the next one is I do math 9 again. Math 9, inverse cosine x, comma root 2 over 2, comma 1. This should do it. Let's see what our calculator gives us. And then we can put the other answer, 0.414. And then the other answer we got was square root of 2 minus 1. Boom. Same answer. But we couldn't have done this by hand. We couldn't have finished by hand. On a calculator, you still got to show all the setups and stuff. All right. The only way you're going to get better at these is by trying them and trying both ways. Not anytime you're like, I don't want to do it that way because I don't feel good at horizontal slicing. Well, it means you should do it. Otherwise, you're going to just stay not good at it. So graphing calculators, we got still show the setup. I'm gonna see if we can pull these off by hand personally. But so we're trying to find this area here. I think horizontal slicing is gonna be complicated because it involves like this two sides of the same curve. I mean, I think we could do it, and then this also, like, and there's like this little sliver here. Like, I don't know. I think horizontal slicing is going to be really hard here. So I don't think I'm gonna try it. But we got to figure out if we do vertical slicing, it's going to be y top minus y bottom. And it's the same top curve the whole time, same bottom curve the whole time. So that's convenient. So it's going to be y top minus y bottom. The y coordinates give you the dimension of that slice. The dx is the thickness of it. It's very thin. But we need to get these into terms of x, which they already are. So y top is sine pi x. Y bottom is x cubed minus 4x. Now be careful. You got to make sure you subtract all of this. Put it in parentheses. The limits are, well, I don't know the limits yet. This is a sine curve, right? And I'm going to use the period of the sine curve is generally 2 pi divided by anything inside. So the period is 2. So this is actually 2, comma 0. And this is, by the way, and this would be 1, comma 0. Okay, so the limits are 0 to 2. So that's the setup. And then you could just put this in your calculator. I'm going to see if I can do it by hand. And I challenge you guys to do it also if you want some extra practice. The answer to sine is negative cosine. Okay, I could do u substitution here, but it's going to put an extra pi out when I take the derivative because the chain rule. So I'm going to divide by pi to cancel it. And that the chain rule, the u substitution would be a bunch of extra work to give you that 1 over pi in front. Minus x to the 4th over 4 plus 4x squared over 2. You got to distribute that subtraction, 0 to 2. So if we plug 2 in, it's going to be negative 1 over pi cosine of 2 pi minus 16 over 4 is 4 plus 2 times 4 is 8 minus 1 over pi cosine of 0, which is not 0, by the way. So minus 0 plus 0. I never just not write the zeros, assuming it's all going to be 0. That's a 1. So cosine of 2, by the way, is also 1. So this is going to be negative 1 over pi plus 4, and then plus 1 over pi. And these guys are going to end up canceling each other out, and the answer is going to end up being 4. Now, if I had a calculator on test, I would totally do it. I'm just doing this to challenge myself to be better for when I don't have a calculator. But on my calculator, I would do math 9. I can do this all right here. Sine of pi x minus x to the 3rd plus x to the 4th, comma x, comma 0, comma 2. Oh, shoot. Let's see. What did I do wrong? Better be in radio mode. Let's check my radio. Yeah, I'm in radio mode. Did I enter anything in incorrectly? X to the fourth plus. Oh, no. That's not supposed to be x to the fourth. That's supposed to be 4x. There we go. We got it. Now, trying to do this with horizontal slicing. Now, here's another. This is just a creative approach. You guys know that this area is the same as this area, right? So we could just plug it in there and be like, oh, we're just trying to find this area, which is really just vertical slices like this. It's going to be 0 minus x cubed minus 4x, 0 to 2. This should give us the same answer. And the trig is just out of it. And this is just a special case. So that's going to be 16 from negative 4 plus 2 times 4 is 8. Same answer. So this is just a creative approach. I don't even want to tackle the horizontal slicing on this one. Okay. I guess another way we could have found these points, these are obviously x-intercepts for this graph, is setting equal to 0 and solving. Just throwing another option out there. Now, the negative 2 would be way over here, but okay. Okay, let R be the region in quadrant 1 and 2, bounded by that function, and the line y equals 2. Find the area. Now, one thing you could use your calculator for on these is to get a better idea of the sketch. So even with the calculator, you gotta have a visual of what's going on. I mean, I could probably roughly sketch this. This is quadrant 1 and quadrant 2. That's a rational function. This is just a horizontal line, so that's easy. This is a rational function. If you, as x goes to infinity, positive or negative, this is going to go to 0. So it's going to have a horizontal asymptote. Even with the graph, you might not be clear about that unless you think about it ahead of time. There are no vertical asymptotes. Even though there's x's in denominator, there's no way you're going to get division by 0 because x squared can never equal negative 1. When you plug 0 in, you get 20. And the bigger the x's you plug in, the smaller it gets. So like you plug in 1, you get 10. Plug in negative 1, you get 10. You plug in 2, you get 4. You plug in 3, you get 2. So it's just getting smaller and smaller and smaller. Kind of looks like this, kind of like a bell curve. But you graph this on your graphing calculator and make sure to help you out. But still, you got to be thinking about things that should make sense. Y equals 2 is a horizontal line. So we're trying to find the area between these in first and second quadrants, which is what we have there. So we definitely need to find the intersections of these two curves. And so that'd be 20 over 1 plus x squared equals 2. So it's going to be 20 equals 2 plus 2x squared. It's going to be 2x squared equals 18. It's going to be x squared equals 9. Square root, both sides, plus or minus. We actually want to use both of them this time. This is positive 3. This is negative 3. Comma 2, comma 2. If you plug it into either equation, you get that. So those are our intersections. If we do vertical slicing, we can do y top minus y bottom. So vertical slicing, y top minus y bottom, dx. our limits are -3 to 3. Y top is that function there, the 20 over 1 plus x squared. Y bottom is 2, minus 2, dx. So then we would integrate this. Now, this, I know you can use a calculator. I would challenge you to see if you can get away without a calculator, okay? The antiderivative of this that's inverse tangent. And then we would plug 3 in. So it's going to be 20 inverse tangent of 3 minus 6 minus 20 inverse tangent of -3 plus 6. And then just to kind of help you figure it out, inverse, if you're looking at inverse tangent, it's saying, what angle would you get when you plug in? Now, tangent, if you think about it, is an odd function. It repeats itself. It looks like this, right? And if you plug 3 in, you get the same thing as -3, but it's negative. So we're going to subtract. So what I'm trying to say is that 20 inverse tangent -3 is actually -20 inverse tangent of +3. So we could use that to simplify this answer. And we got to distribute this negative, so that's going to become plus. So it's going to be +40 inverse tangent of 3. And you have a -6, another -6, -12. That's the exact answer without a calculator. Now we could plug in our calculator, we could plug in the original, see if we get the same thing. Plug this in, see if we get the same thing. Let's try it out real quick. So 40 inverse tangent of 3 minus 12 is 37.961 or 37.962 if you're really in a rounding. Let's try the other. Math 9. 20 divided by parentheses 1 plus x squared minus 2 comma x comma -3 comma 3, and you get the same answer. Pretty cool. Another idea just to throw out there is that this graph has symmetry on it, right? Isn't the right half the same as the left half? So you could use symmetry instead and say that the area is equal to double the integral from 0 to 3. Right? This should work. Now you would say, okay, it's double, antiderivative is still going to be 20 inverse tangent of x minus 2x, 0 to 3. You plug in 3, and then you plug in 0. Now, inverse tangent 0, what angle do you plug in to get tangent 0? Well, what tangent sine or cosine? So what angle do you plug in to sine? Principal values, that's going to be 0. You're going to get the 40 inverse tangent of 3 minus 12 answer. Same answer, right? But then you didn't have to worry about the whole properties of tangent, inverse tangent, even function, or odd functions. Now, the other way is to do horizontal slicing. Let's just see if we can figure it out. Horizontal slicing is going to be x right minus x left dy. The limits, this is a little funky, the lower y limit is 2, the upper y limit is 20. It's not even an intersection, but it's where you got to stop. And then x right, you would have to solve this equation for x. So that's going to be, I got to do a little work over here. That's going to be 1 plus x squared times y. So I kind of like cross multiply. 1 plus x squared equals 20 over y. And you subtract 1. And then you take the square root of both sides, plus or minus. And you're actually going to use both of these because the plus is the x right and the minus is the x left. X right and x left are on the same curve. So the right would be the positive square root of 20 over y minus 1. and then subtract. The left is the negative square root of 20 over y minus 1. It's kind of crazy. It's the same curve, right? And then we could, we could clean this up and say, okay, well, minus minus is plus plus. This is going to be 2 to 20 square root of 20 over y minus y dy. Let's try it in our calculator and see if it gives us. Now in our calculator, we're going to put x's wherever the y's are, because that's just the way our calculators work. We only can put x variables in. It doesn't really matter if these are all x's or a's or whatever. It should all come out the same. So we're going to do 2 times math 9 square root of 20 divided by x minus 1, close the square root, comma x, comma 2, comma 20. Let's see. Should get 37.961, just like before. Boom, 37.961. Nice. But I don't think we'd be able to do that one by hand. So after setting it up by hand. Okay, number 8, find the area of region R, which is this region right here. And this is this function. It's kind of this crazy curve. Line L is a tangent line to f of x at x equals 0. If you plug 0 in here, by the way, you're going to get 0, 0, 0. Cosine 0 is 1, 3. So you know that point. Right interval to find the area of that. So let's just focus on R first. R is just the area under this curve from whatever this point is to whatever that point is. This is the x-intercept. That's going to be one of our limits. So we got to figure out what that x-intercept is. Now, can we do that by hand? Can we set this equal to 0? Set y equal to 0 and solve this by hand? I don't think so. So that's one thing we're going to need our calculator for. I'm going to go ahead and put this whole graph, my graphing calculator, because I am interested in, I think, looking at the graph. If all I'm going to do is integrate the function, I'm not going to bother to enter it into the graphing menu. That's just extra time. But I think we're going to need this for several things. X to the third divided by 4 minus x squared divided by 3 minus x divided by 2 plus 3 cosine x, better be in reading mode. I'm going to go to window. I kind of have a rough idea of what the window might be. I don't know, -5 to 10. I mean, we could do -10 to 10, -10 to 10 just to start with, zoom standard, and then adjust it. Now it should look like this graph. There we go, that does. I'm going to change the window. We could do zoom box, create a box around the window. Drag the corners. You hit enter and it resizes it. So, okay, cool. I mean, this also confirms that we entered the equation correctly. But we got to find this x-intercept. That's easy on a calculator. Second, calculate 0. It looks like it's between -2 and -1. I guess -1.5. Okay, let's write that on here. -1.373122, comma. Now it says 1.2 e -13. Well, that's scientific notation. That's the same thing as 0.12 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's the same thing. Essentially, it's 0. It's just not exact. It's not perfect. Okay, so we have that. And so now, to get that area, we need to, I'm just going to write the equation up here. We're just integrating a single curve here. We're going to go -1.373122 to 0 of the function, and it's okay to write f of x if if they named it for you, then you can just put that name in. That's good enough for. And I'm just going to do it on the graph screen. I usually don't do this, but since we're already here, I'm going to do number 7, math second trace calc. Number 7, type the lower limit in. It's really close, but that's not good enough. That's not exactly what we wrote down. So never use, type it in -1. Sorry, yeah, 0.373122, and then the right one is 0, and then it shades it in kind of cool, and it gives you the answer. So I'm going to write that down. It's 2.903094. I'm just writing all these extra decimals down because I might need this for another part later. I don't have to recalculate. For my answer, I'm going to just write 3 decimal, actually rounded or truncated. So that's that part. Part B says line L is tangent. We want to find the area of the integral region S. So that's the area between the tangent line and this function. So y top minus y bottom is the area between two curves. Y top minus y bottom dx. There's a couple things we need to do. We need to know the equation of this tangent line because it's the y top. We also need to know it so that we can find the intersection of these two curves. We don't know that. That's going to be a limit. So we got to find the equation of the tangent line. Now, our calculators can do that, or we could try and do it by hand. I think we could actually do pretty well doing it by hand. You already know the point, so that's easy. You just need the slope. So the slope is going to be f prime. F prime of x would be 3x squared over 4 minus 2x over 3 minus 1/2 minus 3 sine x. And then you're going to plug 0 into it. And it's going to be 0 minus 0 minus 1/2 minus 0. It's going to be -1/2. That's your slope. So this is a pretty easy. And then we're going to do point slope form. Y minus 3 equals -1/2 x minus 0. And we change the slope intercept form. Y equals -1/2 x plus 3. This is the equation of the tangent line. Pretty easy to do by hand. Now, of course, you could take the derivative, on your calculator. Your calculator do the derivative. You could do that other thing I've showed you guys before. Second program draw. Number 5, tangent. And you tell it where you want it to, and it draws it on there, and then it writes the equation down here at the bottom. Now, it's not perfect. It's pretty close. We got the exact answer. So if you did that, just a reminder, if you're in the graph menu, you can do second program, which gives you to the draw menu. And then you go to option number 5, tangent. It takes you back to the graph screen, and you put in the x coordinate of where you want it, and then you hit enter, and it graphs it for you, and it writes the equation at the bottom screen. Y equals -0.4999975x plus 3. So you can do it like that. I kind of need to see evidence of which way you did it. Now, that's good. We can now put, what we could do is we could type this into the y menu now, -0.5x plus 3. So we can graph it. Now, it's already graphed there, but it's not really there to do calculations with until you enter into the y menu. Now, the reason I did this is I want to find the intersection of both of these, right? So I'm going to go second calc, intersect, first curve, second curve, guess. It looks like it's around 3.5. And I'm going to write that on my graph, 3.389867, comma 1.30506662. I just write it all out because we're going to need to carry more than 3 decimals in our work. Okay. Now to find this area, we already said we're going to do y top minus y bottom. So the limits now are 0, x left to x right, 3.389867. Better have several decimals past 3 decimal points in the middle of your work. Y top is the tangent line, 1/2 x plus 3, or however you found it, minus y bottom is this function, x cubed over 4 minus x squared over 3 minus x over 2 plus 3 cosine x dx. You got to put it all in parentheses though, okay? Now, I think we could probably, well, no, we wouldn't give her. We could find the antiderivative by hand, but plugging this in would just be stupid. So what I'm going to do now is I'm going to put this in. I'm going to do this calculation. Our graphs can only do derivatives of integrals of one function at a time. But if we go to this menu, we do math 9. We can do as many as we want. We can do this all in one line. This is, remember, this is y2, and this is stored in y1. So I'm going to do math 9, and I'm going to say vars, y vars, function y2 minus vars, y vars, function y1. And that's exactly all this stuff because I had those stored in the y menu. Comma x, comma 0, comma 3.3898677. This will do it all in 6.981 or 6.982. 3 decimal accuracy. So just reminding you, so I went to the home screen. I'm just going to write this down. I went to the home screen. And I went to math button, number 9, F and int, right? And then to put this equation here, I did vars, y vars, function, and I picked option 2. I think I did. Let's look at it again. Vars, y vars, function. Y2 is number 2. And then for the next, and then I did minus. And for the next one, this guy, I did vars, y vars, function, option number 1, y1. And then I said comma x, comma 0, comma 3 point, dot, 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 dot. So you got to know how to use your calculator to do things really quick and easier. So there's a lot of interesting opportunities on this problem. And be careful if you accidentally did y1 minus y2, it should actually stand out to you because you would have got the same answer but negative, and you should be thrown off by anytime you're trying to find area. If you get a negative, you set something up wrong, you did something wrong for sure. You should never get negative area if that's exactly what we're looking for. When we evaluate integrals, we can get negative answers. But on all these problems, we were actually trying to find area specifically. So this was a really good assignment. I guarantee you're going to have a few problems like this on your next test.